Hi guys, today we're going to move on to our next unit and we're going to start with topic 2.1, classification of matter. So we're going to jump ahead and see what's going to happen in terms of returning back to class. We traditionally move on to a unit that is very math intensive, and so we're going to rearrange a little bit and see how we can make things best work for you. And so we're going to start, like I said, with classification of matter. So I say this in my number of years in teaching chemistry that the first couple of units I call leveling the playing field. I know some of you have had exposure to this, and the amount of exposure that you've had is very different for each and every one of you. So there's going to be, for example, today, this might be review for you, and for some of you, this might be brand new. But as we work through the unit, there's going to be material that none of you have seen, and we integrate it in to bring in that chemistry aspect. Definitely, as we move through the year, we're going to get into things called stoichiometry, using dimensional analysis from a balanced chemical equation. And right now, that may sound like a bunch of gibberish, but by the end of the year, those are going to be things that you're familiar with. So, like I said, we're leveling the playing field. Things will get more challenging and things that you haven't seen before. So just bear with me as we work through these first units to get everybody on the same page. So this is more traditionally what the notes are going to look like, and I have a handout. The handout can work with if you want to use Kami, if you want to print it out, or if you want to just do them in the notebook, but you want to make sure that you are taking notes in some way, shape, or form. So when we look at matter, the most basic building block that we have for which we can classify matter into is built of atoms. There are things that we see in everyday life, and you probably think of something very stereotypical, kind of like here in the Big Bang Theory logo, in that we see the stereotypical, almost solar system like structure of the atom. We'll get into why that isn't an accurate representation, but we're going to stick with it right now. Now, matter is of four states, and there's more out there. Solid, liquid, gas, you're very familiar with. We have plasma, which the sun is considered a plasma, and then we have other things out there like a Bose-Einstein condensate. So there's different states of matter, but most of what we are exposed to on a day-to-day matter is solid, liquid, and gas. The one thing that must be true in order for something to be considered matter is it has to have two different properties. The first thing is it has to have mass. And the second requirement is that it has volume. So it has to take up space and it has to have mass. So there are subcategories, and biology is a really good example in your science from last year, is we like to organize things in science and group things. So in chemistry, we have certain areas that we do this as well. So it's kind of like a hierarchy in life, or the different types of life. This is the hierarchy organization of matter. So the first way we can break down matter is that it can be classified as a mixture. And that's where you have more than one pure substance combined together. Most things you interact with on a day-to-day basis is a mixture. And so right here, it stresses that it's material with a variable composition. So for example, this pitcher of lemonade, if I gave everybody water, sugar, and lemons and said, make lemonade, without a recipe, everybody's mixture, the combination is going to be different. Same thing with the pizza, for example, that everybody could have unlimited toppings and nobody would build the exact same pizza. So it's something that varies in its composition. So we're going to continue with that left-hand side of the organizer, and we can continue to break things down. So the one thing that is in common here is, again, they can vary, but we can break down mixtures into two subtypes. They can either be called what's called a homogeneous mixture, or it's sometimes referred to as a solution, or it can be referred to as a heterogeneous mixture. And so there's a list of kind of three ways to identify something as being homogeneous versus heterogeneous. So a lot of times, like if you think about mouthwash, that's a solution. You have lots of things mixed into that, but if you take a look at it, it looks all the same. If you pour yourself your small dose of mouthwash to use and compare it to the original container, it looks uniform. So the three things that we look for in a homogeneous mixture is that it's the same phase and it's uniform, meaning that it's mixed well. So if you play a brass instrument, for example, you're using an alloy, and that alloy is of zinc and copper. So you look at it and it looks uniform. It doesn't, you can't see the zinc versus the copper. So another alloy is you can take gold and copper, for example. Salt water can be uniform. So if I had 2 glasses of water sitting on a table, one contained salt, the other contained just water, you wouldn't have a way of knowing which is which without tasting. And so again, it's a mixture in that it's uniformly mixed and it looks the same throughout. Heterogeneous mixtures are where you can start to see the parts and pieces. So the Supreme pizza, like I had on the previous slide, is an example of a heterogeneous mixture. If you're like me, green peppers are an atrocity, and if they disappeared on the face of the earth, I'd be okay with that. So you can pick apart that sample. Trail mix is another one. Probably the raisins are the last to be eaten if they're ate at all, and the M&Ms are probably definitely going to get consumed. And so again, it's something that's easy to separate, meaning it's non-uniform. So again, how I distinguish the two is if I imagine that if I take a sample of it, will it be the same or not? So again, with the lemonade, if I pour myself a glass and I compare that lemonade to the original pitcher, it looks the same. That's uniformly mixed, so that would be homogeneous. Again, if I took a scoop of Chex Mix, for example, what I have in my hand is the same components in the original bag, but it's not going to appear the same. You're not going to have the same well-blended mix. You might get more of one type over another, and that would make it heterogeneous. So again, you're just looking at basically how well mixed something is to classify it. Going back to the right-hand side of our setup, we can then classify matter as being a pure substance, meaning that it's made out of only one material of one type. Mixtures, you have 2 or more different pure substances combined together. So in salt water, for example, you're mixing salt and water, making it a mixture. If you were to separate those and have just the salt or just the water, that would classify into the pure substances. And that means that we have 2 types as well. Those 2 types are elements or compounds. So elements, meaning that their most basic building block that makes silver versus sodium is the atom. It's not the subparticles within the atom that makes it. It's the combination of those 3 things. How you know something is an element is it has a symbol. And if you can find it on a periodic table, then you definitely know that it is an element. When you take a look, we have things like carbon. You probably used carbon a lot last year in biology, and it has a symbol assigned to it, uppercase C. Some elements like silver are assigned 2 letters, an uppercase versus a lower, and followed by a lowercase. And then these are what's called monoatomic elements. And I'm sure you can pick up on this. Mono meaning one, and atomic meaning atom. So it's only made up of one atom. Some elements are what's called diatomic. And we're going to actually discuss this more tomorrow when we look at particle diagrams. Diatomic meaning it's made out of 2. There are 7 elements that are this way in nature, and oxygen is one of those 7. So oxygen is always paired up to another oxygen molecule. You never have just O floating around in the atmosphere. It's always bonded, and it's O2. And that's what's called diatomic. And we'll get into why elements do that later on. So again, if it's on the periodic table, it's going to be an element. Now, if you take 2 or more of those elements and combine them together into a fixed chemical formula or a fixed ratio, that makes it a compound. So you can't just put two elements together and say I have a compound. You have to take those two elements and combine them together with their electrons being involved to make it a formula. So carbon dioxide, as you're exhaling this right now, you have CO2. So it's made out of our two elements, carbon and oxygen. So compounds always have a chemical formula. So it takes those symbols off the periodic table and combines them together. Water you're very familiar with, H2O. So for water to be water, it must have a chemical formula. If you adjust this just slightly and change it to H2O2, you no longer have water, but you have hydrogen peroxide. So that ratio of elements decides what formula you get and ultimately what type of properties you get from it. So again, just because they're made out of the same elements, as soon as you change the ratio, you change properties. And so then salt, it has sodium and chlorine in it, has a fixed chemical formula. That makes it a compound. So I have some examples here to take a look at, and it is two parts to it. The first thing is they want us to identify it as a pure substance or mixture, and then we're going to break it into one of our four subcategories: element, compound, homogeneous, or heterogeneous. So I have a few hints that will help you as we work through these. So the first one is sodium. And I notice here, and I don't know if it's a typo. Nope, it looks like the font was doing this, where it turned this into an uppercase. This really should say Na. So when we take a look at that, it has a symbol. And so that means it's on the periodic table. And so that means it's an element. If you take a look at your flow chart, elements are a type of pure substance. Okay, so it doesn't matter if you take that sodium and cut it apart. No matter how much of that sodium you have, it will always contain the same atom, making it an element. Sweet tea, if you look on the periodic table, you're going to be looking a long time. It's not there. It doesn't have a chemical formula, so that means it is not a pure substance. That means it's a mixture. If you envision pouring yourself a glass of sweet tea, your glass will look uniform compared to what was in the pitcher. So it's uniformly mixed. So that's going to make it a homogeneous mixture, and we can just abbreviate for that. Table salt, if you take a look, again, this had a little issue with the font, but we have a formula, NaCl. So we know that there's multiple symbols there because we have this breakdown of the uppercase, lowercase. So we have sodium and chlorine. So we have two or more elements, so that eliminates element. And we have a chemical formula. Therefore, it's going to be a compound. And pure substances would be what the classification it breaks into. Vegetable soup, again, it's not on the periodic table. It doesn't have a chemical formula, so that eliminates pure substance. That's going to make this a mixture. If you don't like a certain part, like the carrots of the vegetable soup, you can pick those out and pitch them. So it's not uniformly mixed. So this is going to be heterogeneous in appearance. Water, it's not an element of the periodic table, and it does have a chemical formula, much like example C. So that's going to be the same idea, that because it has a chemical formula, it's a pure substance, and specifically it's a compound because it's a formula of two different elements. Now in example F, we're taking two different compounds. We're combining salt with water. Again, if you think about this, if I gave everybody salt and everybody water and they had to make their own concoction of salt water, not everybody's would be of the same salinity. So that means this is not a compound. These are not fixed in a fixed ratio. So this means it's a mixture. And I would put this in the homogeneous category. Now, if you get too much salt, then that becomes to the point that it's saturated and you get material that settles out. That's a whole different concept. But what we're looking at is it should be able to dissolve and become well mixed. Coffee, so imagine pouring yourself a cup of black coffee. It's not an element of the periodic table, and it doesn't have a chemical formula. It has many different components like caffeine, which caffeine is a compound, and so we're combining different things together. Therefore, it's a mixture. If you think about it, you take the pot of coffee and pour yourself a glass or a cup, really. If you take a look at that, it's in the same ratio as what was in the pot of coffee, so it's well mixed, so that should be homogeneous. So the last one, air, and this one seems to trick a lot of students from year to year. So the air that you're breathing is not fully oxygen. We don't want it to be fully oxygen. If you think about it, oxygen is very flammable, and that would not end well for us. So there's many things in our atmosphere. Nitrogen, and nitrogen is one of those diatomic elements I mentioned before. That's our main component. But we have things like oxygen, carbon dioxide. There's trace amounts of helium and neon. There's sulfur dioxide that's being released from volcanoes and factories and things like that. So there's a lot of things in our atmosphere. There's water vapor and that. So it kind of the list goes on here. So what I'm trying to get at is you can see that it's a lot of different things. It's not just one chemical symbol, so that eliminates element. It's made up of elements and compounds. So that isn't a compound because it's not just everything fixed in one complete ratio of this many nitrogen to this many oxygen. So therefore it must be a mixture, and I would put this in the homogeneous section. Okay. So this is what I'm looking for today is, can you classify something as pure substance mixture? And then can you further break it down into element, compound, homogeneous, heterogeneous? If any of this was confusing to you, if you need something clarified, you need more help, please reach out to me. We can set up a Google Meet. We can talk via Google Hangouts or just send me an email. Otherwise, good luck with your homework. And again, let me know if you have any questions.